So my talk today is going to be hopefully short and sweet about how we have at this very strange conjuncture where we have AI, ultra-fast structural aligners, and AlphaFold that have been coming up and affecting our resource, which is CATH. I don't know if you've been familiar with it. CATH is a protein structure classification database over the past 25 years, 30 at this point. Classifies protein domains into homologous superfamilies related by evolution. This is a very simplified workflow of what we do. Every week we ping the protein data bank, we identify domains, we assign them to CATH superfamilies, most of them automatically. If it's not possible, we have a team of expert curators that they assign them correctly to it. But we were cruising alongside PDB quite happily for 30 years, up until 2 years ago when AlphaFold, on my birthday, decided to gift us 15 years worth of structures in the first go. And the first release was for 365,000 protein chains for 21 model organisms. Then you had subsequent releases for SwissProt and NTDs. And the latest release covers the whole of UniProt. So between 2020 and 2021, we did a pilot work where we started looking at classifying the first release, the 365,000 protein chains. This amounted roughly to 700,000 domains, so almost twice the size of CATH. But if we look at the distribution of, take this plot, the only thing I wanted to take from this plot are 3 points. When we looked at the quality of the data, roughly 50% wasn't very globular, or we couldn't classify it into CATH. The other point is, most of them, 73%, they resemble something that it's already classified in PDB. And the quality for things that are closely resembling something in PDB, they tend to be much higher than things that are remote homologs. And then the additional domains that we could bring in, they are either assigned by new machine learning-based methods or simply by sheerly scanning them with FoldSeq, which is this ultra-fast structural. So this was our first look at the data. But then if you look at this plot, this is a distribution on a log scale of the data that we have over the years. So you can see here, CATH slowly growing and progressing alongside PDB, but now you can see the growth of AlphaFold database reached basically the same size of Tremble. So we have almost 600 times the amount of data as before. So when we started looking at this, we realized that first, when this release of AlphaFold was released, the pipelines that we created at the time, they weren't really up to task. We created this CATH assign, and it wasn't really scalable to that level. So what we did, we rewrote the whole thing from scratch using Nextflow. And to address 2 of the issues that we found in the first release of AlphaFold is that we were looking at finding consistent and high quality domain boundaries to extract the portions that are globular. And then we came out with some other machine learning-based predictors based on embeddings to predict the superfamilies from the get-go. So the first step to address that, one of our PhD students, Jude Wells, developed Chainsaw, kind of a fun name because it sees domains on a protein chain. And it's a 2D to CNN with an architecture based on Chiara Rosetta. And it takes information from the residue distance matrices, secondary structure membership, and it gives us information on can a residue be in this domain or not. And we trained this, but while at the same time we were working on this, we were planning on applying it on the whole of AlphaFold, we realized that just across the hall, the team of David Jones was working on another tool, doing exactly the same thing. They were going to do the same thing as well. Their tool works very well. They even borrow some modules from AlphaFold itself, including the IPA module, the invariant point attention, and they use a different training scheme, which is an affinity learning trained with balanced square affinity. So with this, we decided to collaborate together and try to classify the whole of AlphaFold into CATH and looking how the data looks like. So we created this team to work on this, and with lots of talent and a healthy dose of naivete to go into this, because I think this is an actual sentence that came up at some point. So because we thought this was going to be easy, and actually we were at it for at least a year and a half at this point. So working on this, we created TED, which is the Encyclopedia of Domains, where we went and we segmented the whole of AlphaFold database into constituent domains. the first step is we basically separated TED into two data sets, TED 100 and TED redundant. So we looked at only at structures that they were 100% sequence identical. And then we used this consensus-based approach that combines Marizo, the tool from David Jones, Chainsaw, and then a biophysics-based predictor, which is Unidoc, to come up with a sensible domain assignment in this case. So using this consensus-based domain approach, basically we have either 3 domains predictors agree, 2 out of 3, or only 1. And then we carry forward only the ones that agree at least twice, or all methods agree at the same time. So when we started classifying these domains and realized that using structure to look for structure works better. If you notice here, we get roughly 370 million protein domains in CATH, which is in TED, which is almost a 600-fold increase compared to what we had before. But we vastly outnumber sequence-based approaches, such as PFAM or even our original CATH G3D, which is based on leader Markov models. But let's go back to that first slide I showed you where we did that pilot work. So I claimed that 50% of the data was wrong in AlphaFold. Technically, that proportion is much lower. The issue was we were using hidden Markov models at first to look for these boundaries. We realized that the quality, we weren't really looking at the actual domain. Sometimes we were struggling a little bit, and that would bring down the PLDT quite a lot. So the average PLDT for the domains in TED at this point, we are either high or very high. We have roughly 90% of the data that looks very well. So the next step, once we identify these domains, we use a 2-track approach to bring them into CATH. The first one track is using a sequence clustering using MM6 at 50% sequence identity. And then we use FoldSeq and an in-house tool called FoldClass, which is based on structure embeddings built by David Jones, to label all these domains within the clusters. We realized that then we ended up with 79 million clusters containing roughly 251 million domains that have a CATH label at this point. It could be at the homology level or at the T level. And then we can see that these clusters, they vary quite a bit, both in size and also in quality of the notation. We can see that when you look at non-singleton clusters, roughly 21%, they are all labeled with the same CATH superfamily. Sometimes you can go to partially labeled or unlabeled. But while we do have a lot of singletons, there are also clusters that they have almost 12,000 domains in them. So one of the things we expected, and we noticed in the first release of AlphaFold, is that superfamilies that are large already in PDB, they would expand consistently. Because being trained on PDB, we would expect to find this enrichment in the signal. So superfamilies that were large in CATH, they actually expanded quite a bit in TED. But remarkably, we also found some other superfamilies that maybe they had 1 or 2 representatives in PDB, that now they have tens and hundreds of thousands of members in it. And this is going to be particularly useful because if you see here at the top, you have the MFS general substrate transporter like. This is an antibiotic efflux pump. So we could start looking at these things for drug repurposing in the first place. So more details on this tomorrow. I have a talk of 3DC where we're going to look more a bit about the biology of this. But the next step, once we had this information about domains assignments, Sean in David's group started looking at what are novel interacting superfamily pairs. That is, we're looking at how domains within the same chain are interacting between themselves and in which orientation they interact at this point. You can see here at the bottom, this is, I'm going to blow it up in the next slide, basically. In this case, you can see the superfamily NTRC-like domain protein in PDB. It's only found interacting on the top left portion of the domain, and it's only found in that particular conformation. If we look at this particular orientation of the domain, you can find it interacting with a lot more different superfamilies and in different orientations around the domain as well. So this could be interesting to look at PPIs as well. So if you remember those domains that didn't map to CATH, those were roughly 80 million domains that included also singletons as well. So then we started looking at, are these potentially new folds, or are we falling back to that issue of, are these domains of poor quality? We started using this clustering approach, and then we stripped out all things that were low quality. We scanned them against PDB and a large set of other databases, including ECOD, SCOP, and SCOP. And then using a novel predictor that predicts, does this protein looks like something we saw before, we can reverse this score and use it as a novelty score. Does this look like something we haven't seen before? So, is it moving? Yes. So by using this approach, we found roughly 60,000 novel folds. Some of them they're just novelties. You can have very small clusters, like with one protein in it, or just one domain. But sometimes you have some other ones that are actually highly rich. You have almost clusters with a size of 8,000 or 20,000 as well. Then when we started looking at the symmetry of these domains, we also found some new repeats as well. You can see this highly symmetrical domains. I think we're going to make t-shirts at some point, or mugs at least. And we can go all the way from these extruder repeats, that we call kind of floating pegs, all the way to an 11-fold beta propeller up there, that there are like at least 500 in AlphaFold that we found. So to come down to the availability of this code, the new CATH AlphaFlow, it's entirely written in Nextflow, so anybody can use it at this point. It's publicly available. You can have custom workflows to download structure from PDB, from AlphaFold directly. You can go straight from the structure, from the ABI, all the way to the annotations. It's very fast. This is our worst possible case scenario in our HPC, where we get one CPU, 1 gigabyte of RAM. We're able to process through 100,000 structures in 1 hour. So it's really good. And then all the modules that can be used independently. So if you're just interested in, do I want to know the globularity of this protein, or the PLDDT, or the CATH assignment, you can use them individually. Then in the background, Ian, in our team, which is our lab manager, who's been working on this new resource, which is going to be a new CATH website, where you're able to, at the moment, you can put in your UniProt ID. This will retrieve the structures from UniProt and then assign and show you all this data. It's based on a fast API stack, and the idea is you can download our full raw data from Zenodo, which is only 100 gigabytes, and then you can run your own instance of the web server on your own computer if you want. This lets you kind of use your data locally for whatever reason you want. The data is also available through an open API, which is 3D Beacons compliant. So for every single model, we have information about segments, and this kind of interplays very well with other resources in 3D Beacons, such as PDB and Swiss model as well. And this is how the website looks like. This is one protein here. You can see the domains alongside the chain. You'll have a CATH assignment if available, the length of the domain, their average PLDDT, some packing density statistics. And now we're looking at implementing those interacting superfamily pairs in the interface as well. So all this data and the protocols, now we're also applying them to the next release of CATH. We decided to make a big jump. CATH went from 4.1, 4.2, 4.3 up until 2019. In September, we're going to release CATH 5. I think it warrants an actual big release this time. We are going to be up to date with PDB, because at the moment we're back in, the data is back from 2019. This doubles the number of domains that we have in CATH from 500,000 domains to 1 million. I'm currently regenerating the functional families using 2024 data from UniProt, including structural representatives from TED. And all of this is being run through AlphaFlow. And if you want to read a little preview on how we're going to expand CATH, we have a new paper in JMB as well. Okay, and this is the team behind all of this work. And if you have any questions, please let me know.